Well, greetings, Selectron fans. It's finally time to talk about how to read data from this tube. The sequence you're watching is similar to previous videos in which I'm writing ones and zeros, and the only reason you can see the phosphor glow is because the read plate has been held at a large positive potential. To do electronic reads, we're going to have to set this at a negative potential, which means you generally will not see this beautiful green glow. Bear with me for a minute. I'm going to reprogram my microprocessor. When it's reprogrammed, you'll see a little pulse of light. And then, believe it or not, we are actually writing and reading from the tube, although there is no visual indication. So we may as well turn the lights on. So in this video, I plan to show you how I do a memory test. This is an example where I write all zeros and then read back all that data and see if there's any errors, and I'll just cycle through and then write ones and then read all 256 locations and report any bad locations, bad data. So this will cycle through infinitely. The other part of this video is I'm going to show you my electronic solution to reading from the tube, sort of the physics behind the tube and the electronics and why I chose what I did. And part of that will be explaining some of the signals that we see. Now, what you see there, the circuitry is reading zeros as it was reading, and then we'll wait for it to come around. Now we're reading all ones, so you can kind of see the difference in the signals that we're expecting. So I wanted to remind everyone of the potentials that I'm using in this tube. My cathodes, which are the source of our thermionically emitted electrons, are biased at 0 volts. This provides the reference. Selection bars are at 0 volts, typically in the idle state, except for when we need to deselect deselect the bars, and then we would apply 0 volts to the correct bars for selecting an address. The collector always sits at 180 volts. The eyelet, which is completely isolated from everything, will find itself at either 0 volts or 180 volts, depending on what was written to it. The write plate typically sits at 0 volts, except for during the write process, obviously, in which we pulse 360 volts. And the whole selection and pulsing of write plate was discussed in the write video, and this is how we, by doing the timing just right, we can either have a 0 or a 1. Now, on my little cartoon over here, I've got this guy showing electrons going through. So this is at 180 volts. This is, I would associate with a digital 1, 180. This guy, I have electrons kind of turning around. So this is going to be near 0 volts, and I associate that with a low. Now, we come to the read plate. The read plate up till now has been 100 volts. This would allow any eyelets that were 180 volts or high to allow that electron current to come through, hit the phosphorus screen, make a little pulse of light, and we can see this little glow. In the write process, this can't be our idle state anymore. It now needs to be minus 100. And I apologize, I believe that's meant to be positive 150. So this now is the new normal, the idle state of the plate. So that means we will not get to see a phosphor glow from any high bits here with this thing at minus 100. It's going to reject everything. The way we're going to do an electronic read is this read plate sits at minus 100 volts, and then we are going to pulse this to 150 volts. That would give me a pulse of current from any bit that is a high. I get a pulse of current. I get a lot of secondaries off of this back screen here. And then we're going to try to pick up current with these read sense wires. The way we're going to do this, our Faraday cage is biased at 500 volts. We need to add approximately positive 100 volts to the read sense wire so that we're actually attracting these secondary electrons. The game plan is to take whatever pulse of current I get when I pulse the read plate. We're going to try to amplify that. And then what we're going to do is send this to an RS or an SR latch, however you want to say it, so that we can pull the state of this at some point. So let me finish drawing this. Set, reset, output Q, output not Q. So what we're going to do is we're going to take a digital line from my PIC microprocessor. We're going to reset this RS latch. I pulse my read plate. If I get a little burst of current, then hopefully, if we've done everything correctly, we will set this latch, and then it will be a matter of reading the state of this output back to my PIC microcontroller. So that's the game plan. So now I want to go through the basic electronics, how we set up potentials on the read sense, and how I actually detect this pulse of current that I get from our read sense wires. So I start with my 500 volts, which is applied to the Faraday cage, and then we need to add another approximately 100 to 200 volts to apply to the read sense wire. And what I do is apply 12 9-volt batteries in series. So we have 12 9-volt batteries in series. All of this that I am drawing from this point forward is in a shielded box. I didn't leave a lot of room here for my resistors, but we need two resistors. Let's just right over that. And then another resistor right here and to the read sense wire. I have a capacitor. So these two resistors are important. It allows this read sense wire or the charge to pulse without the power supply is trying to absolutely maintain that potential. This first 68K and this capacitor here form sort of a basic low pass filter to kind of get rid of high frequency noise. So what we're expecting from this read sense over time is a pulse of negative current because it's electrons whenever I pulse my read plate. The data sheet says this should be in the range of 20 to 40 microamps. So the goal here is to measure this current directly. And when I say directly measure current, I mean we're not going to put this pulse across a resistor and then try to measure a voltage. It would be better if we just used an ammeter or the equivalent thereof. So what's going to happen? Let's put another capacitor here that's going to block the overall large DC, and then we're going to put this into a basic op-amp circuit. Not really leaving room for my resistors here, but this thing is called a transimpedance amplifier. So basically, the output is related to the current in by this feedback resistor. Since I'm expecting 20 to 40 microamps, I'm going to put a 100K here. So basically, V out equals minus 100K in. So with 20 to 40 microamps coming in, and this will actually be a negative because it's a current electron pulse. My V out will be on the order. V out will be 2 to 4 volts positive going using this. Now, the reason I'm doing this node right here, as long as my op amp is fast enough, this is a virtual ground. It's 0 volts. So that means that this little current pulse that I'm talking about, this little pulse of electrons that we've got going here, this path is a lower impedance path than trying to go back any other direction. So this is what I mean. We're trying to measure current directly and as efficiently as possible. This capacitor here has the same value. This current pulse, in my LT-SPICE simulation, we can simulate this as a current source going to ground. So that's how I would sense this point, or excuse me, this is how I would model this circuit in LT-SPICE. I would just put a little current source going to ground. So let's have a quick look at the full schematic of my read detection scheme here. So I start again with my power supply for the Faraday cage. This V4, the 100 volts, represents the 12 9-volt batteries in series. And then I have my RC network that I mentioned before. Here's our little read wire sense. This is where the pulse of current is coming in. And I would expect some, again, a little pulse of negative going current. This would be something on the order of 20 to 40 microamps. And then the output of my transimpedance amplifier, I'm going to sort of sketch in some of the noise that we might see whenever we do this. And I will show you proper oscilloscope graphs in a minute. But this potential here is going to be anywhere between 2 to 4 volts, depending on which bit we address. It is extremely variable, and I will show that to you. I go ahead and filter this a little bit, provide a little bit of gain, and then finally I have something that looks like this on the output here. We've got our just a little wiggle, and then something that might look like this. And then this, because this is basically a times two amplifier, this is going to be anywhere between four-ish to 8-ish volts. It is variable. It depends on which bit address we're addressing as to what we actually get. So the way I decide whether, this is a 1 or a 0, I need to establish that I have a current pulse, because if I'm reading a 0, I basically have nothing here, right? So I need something that will discriminate against noise, but if it's greater than some value, we will say that it's a 1. So what I'm going to do is use this unused half of my LM1458 op amp as a comparator. I set up a basic voltage divider that's going to establish some potential where we say if my pulse is greater than this potential, we're going to say it's a 1. If it's below, we're going to say it's a 0. So I'm using this guy as a comparator. And then I have a little R resistor and Zener diode. I think this is something like 6.3 volts, if I recall. But I'll get a pulse between 0 or 6 volts, depending on whether we're marking this as a low or a 1. This set gets sent over to a simple RS latch. I'm just doing this with basic transistors and resistors. So that set gets over here, and then finally, our pick. Remember, our reset needs to happen before we try to pulse the read plate. So this comes from my pick, one of the output lines. And then we are going to pull the output. This is Q. We're going to pull the output here and read this in with a pick. And we do it, and again, we try to do this somewhere in the middle of this pulse if it had happened at all. Well, so let's go through the expected timing of all the pulses that we'll need to handle. The first of which is the selection bars. So we don't do anything until we've selected the correct bit. Before we start the read or write process, the selection bars are at their quiescent point, the idle state, where they're at 0 volts. So then we want to start this read process. We're going to deselect the bars that we don't need, select the ones that we need for the right bit address, and then what's going to happen sometime after I've made this selection, I'm going to make sure to reset this RS latch that I mentioned earlier. So we reset that. This comes from the microcontroller, then the read plate. So a little bit of time after that, we are going to take our read plate. We're going to go from an off state. Remember, there's no visual indication when it's like this. And then pulse the read plate on. Now, yes, if the bit is high, we would be able to see, possibly, the phosphor. But this is only 100 microseconds long, this pulse. So we're not going to see this. This is too short. So during this read plate pulse, I would expect some kind of a current pulse, assuming that the bit is high. So if the bit's high, I expect a current pulse. This is out of my transimpedance amplifier. And I mentioned this would be somewhere between 2 to 4 volts. Of course, if it's a low, no current, we would get none. Now, you may have noticed in the very early introductory video that there was noise at some of those scope traces. The process of selecting and deselecting, there's inner electrode capacitances. We're going to see a little bit of this noise, and that's why there's some timing delays on all this. So this is again our output of our transimpedance output. Once I've reset this, and if I have a current pulse sufficient to trigger my RS latch, what I do at this point, before anything else happens, is we pull the output of the RS latch to see if it's high or low. And this is where we get our data back to the PIC. After this, we go ahead and pulse the read plate back down to its idle state, and then turn everything off, and I get a little bit of noise and that sort of thing. So we have our memory test module kind of going on right now. What I'm doing is I'm writing ones to all memory locations. So it's going a little slower than I normally would. But I wanted to show what the typical signals look like when it starts reading the information back. So these are all highs or all ones, and you see the pulse of current there straight from the transimpedance amplifier. That's the yellow. The blue curve is after the filtering and the gain of 2. So you can. One thing I wanted to point out was the extreme variability in the pulse height or the amount of current that you get. It's not every bit is the same. There are some that are much larger and much smaller than the average. So this is going to be an issue when we start looking at failed bits. It's most likely because they're not producing much of a current pulse. So those are the memory addresses that were read as bad, air quotes. Now we're writing zeros, and we're going to go back and see what the zeros look like. So let's have a look at the read signals when I know there's zeros everywhere. And you can see there isn't a pulse of current when I pulse the read plate. The level pretty much stays the same. Now you may notice the traces are jumping up and down a little bit. That is a 60 hertz hum from a power supply. It's amazing that this tube is working as well as it does with this dirty power supply. But that is sort of a demonstration of the signals that we would get. So I have my memory test module going as fast as I dare. It's going a lot faster than it was. We're going through all 256 bit locations in about a second-ish read write. And what I'm doing is I'm keeping track of those addresses that return errors. Not every bad place will report an error. This is sort of a noise thing, but I'm just going to let this go, and if an address shows up as being bad, we're going to remove it from the list of good bit locations. So this is not unlike a bad sector table that one might have found in early hard drives. So this is going to be the approach. We're just going to let this go and document all of the bad addresses. Now that we have our list of bad address locations, we'll just avoid them when trying to write data to the tube. It's now time to try to write meaningful information to this tube, and I propose to send short ASCII encoded messages to the tube and see if we can retrieve them. So let's see how we go. So here I'm writing a message to the tube, and then I'm pausing a little bit to read it back. I've got the replay speed going at 0.5% because I can't talk as fast as this thing is going, but that's the message that we saved and then retrieved. Hello world, my name is. And it's clear that there is some bit information, but part of this process, I go ahead and turn on the read plate. That's the first 128 bits. This is the other half of the stored data for that message, discounting any bad bits. And then we're going to come around. It turns off that read plate, and then we reread the same data. We don't write it. Then we reread the exact same message. It was stored in the tube. And then we just sort of cycle through this again, rewrite the data and reread it. So I'm replaying the same clip at normal speed just to kind of give you a sense of how quickly this went. So I write the message, read the message. I show you the first 128 bits, the visual indication, by turning on the read plate. The other half of the information, the upper 128 bits, come back, turn off the read plate, come back down. I reread the data to see if it's changed. I'll mention, we're going to let this cycle through again. And then I rewrite the message and then read it back in after some arbitrary amount of time. And clearly the M is corrupt. I must have missed a bit during the memory test situation. Again, the back side of the memory tube, this is the upper 128 bits. Turn off the read plate. We can do that at pretty much at will. And then we're going to just repeat this. I'm going to write the message, read the data in at some arbitrary time. This thing is just going, looping. Hello world, my name is SB-256. And this read plate off and read plate on stuff is when I was manipulating the read plate to give you the visual indication. But this is key. I reread the data without writing just to see if it's changed. And it doesn't change, so then we just kind of repeat this process. So I've changed the scene a little bit so that we're not having to pan the camera back and forth. I also made a few adjustments to the threshold and to some rating timing delays. Apparently these changes were not in favor of good data. So I'm showing you this clip to show you what I read is what I get. This message isn't stored in my microprocessor. It is stored on the tube, and I read back what I get. Sometimes it's gibberish. Sometimes it's closer to what I intended. But I'm going to make some more changes and see if we can make this a little bit better. So I've made some changes to the way I write. I've changed some of the delays in the sequence. The sequence to write data to this tube is quite complicated. You have to do it in a certain order and with certain delays to allow things to happen. You might see my writing video, the write process. At any rate, we seem to be circling an answer that makes this tube perform better than it was. That's not to say that there aren't some errors in this. And as I, kind of play around with this tube, the only thing that really made a difference or seemed to be an issue is, the pulse current that you get from each individual bit varies quite a bit. And it's unfortunate that this tube didn't get to enjoy the years of research and development to make it more reliable. That said, magnetic core memory was invented, 3-ish, 4-ish years after this thing. Magnetic core memory out of the gate was more reliable and easier to manufacture. The inside of this tube is very complex and quite complicated to produce. So sadly, magnetic core memory took off, and this type of technology kind of died before it got to develop. Now that we have our read circuit working on the breadboard, it's time to manufacture a printed circuit board, wire this thing up, and get it installed into a shielded box. The shielding will help mitigate interference and hopefully will perform better. But it's time to close this thing up. Well, thanks for following along so far. We were able to demonstrate that we can write and read to the tube as it was intended. I'm going back to this old shot where I'm writing ones and then zeros, and then it occurs to me we basically have on one side 2 8x8 arrays of indicators, so we could use it as a display device. Using the Selectron as a display device isn't without some precedents. The inventor actually published an image in one of his reports, here we're getting to it, And we will use this as inspiration for our display. So knowing the address for each bit and associated phosphor, we can build a simple font set, if you will, and spell out Selectron. We're doing this sort of 2 letters at a time, but there you go. So we've managed to demonstrate the operation of this tube, both its intended function as a memory tube and sort of a little a fun side here where we're using it as a display device. So with that, I thank you for watching and thank you for playing along.